There we go. Good morning, everyone.
How's the audio, Steve? Can you hear me all right?
I can hear you just fine. All right, sorry everybody, we're having a couple of technical glitches getting up and running, but we are in the zone now. How is everybody doing today? Thumbs up if you're doing excellent.
You can hear me now?
Yep.
All right. And I can't really hear any of you yet. Steve, can you say something?
I am talking right now, so I'll be
loud and clear.
Calling in from New Mexico today. So James is actually going to be leading our tour. So James and I are the support engineers for the mechanical engineering department. Our job is to facilitate the hands-on learning. So we fix, maintain, upgrade all the undergraduate teaching labs. There are 6 of these labs and project courses that you'll be interacting with as required parts of our program. Because as engineers, when you really break it down, we're using science to solve practical problems. If you don't know how to solve practical problems and put your hands on things, you won't be as good of an engineer. So all the stuff that you're going to see on the tour today is not only stuff that's available to you, but things that you're expected to use. Because if you don't know how to turn the wrench, do the CAD design, acquire the data, understand how to transfer the heat, make the dynamic linkage, you're going to be limited as an engineer. And these are tools that we put in your toolbox so that you can succeed as you go into either further research or industry. So James will be guiding the tour today, and I'll just be kind of filling in, answering questions as we transition from lab to lab. So James, take it away.
Thanks, Steve. Welcome, everyone. Where I am sitting right now is our Emec Laboratory. And this is a really fun lab to start in for a couple of reasons. The first one is this is one of the one of the first introductions to a lot of the fun tools that mechanical engineers get to use to solve problems. And so one of the things I'll start with, it's always good to start with a big fancy toy. So behind me, you can see a 3-axis CNC mill. And this is a tool that is used across many industries by mechanical engineers to solve problems. And some examples of things that we've worked on even in the last month here at the lab include making a specialized furnace for heating up steel to make knives, prosthetic devices for a young man who needs a very custom prosthetic to help solve problems that he is experiencing, and a number of other applications as well. I'm sure Steve could name 1,000 things. He's sort of the resident CNC expert. But you won't start there, because to understand how to make something with the CNC, you have to understand the fundamentals of how to make things. And so in Mech 200, we start by teaching you how to measure things. And we would use a tool like digital or dial calipers like this. So this allows you to make very precise measurements of length. We also have tools for measuring things like flatness and thread pitch and 1,000 other little details that help to make you really good, not just at understanding the theory behind what we're measuring, but the practice of actually measuring it. And that's sort of the heart of the CSU program in mechanical engineering, is marrying the coursework that you learn every day in the class to real-world experience to make you both competent with a pen and paper and in the machine shop. And so once you have the fundamentals of how to use hand tools, files, the dial caliper, even good hammering technique, percussive maintenance is a staple in mechanical engineering. I can't tell you how many times I've fixed, a multi-million-dollar engine test cell with a hammer like this. It's not knowing how to swing a hammer, it's knowing where to hit. That's the chief thing in mechanical engineering. Once you've learned the hand tools, you graduate to something that's a little bit more fancy. So behind me on this side is a manual lathe, and this is a machine tool. Let's see if I can get it. Oh, 1 second. It is a tour after all, and since you can't be here with me, though I desperately wish that you could be, because this place is awesome. We'll see here. So I've got my whole computer. So if I drop it and the screen goes blank, you know where I've gone. So this tool is called a lathe, and essentially what it does is you put a piece of material, point the camera here, in this thing. It's called the chuck, and it spins the whole piece of material, which it's in gear right now, so I can't show you that. But it spins the piece of material. So you can see we turn brass. There's like brass shavings and steel, aluminum, plastic. It can work with all kinds of materials. And then you mount a tool in this piece here, and you can carve a shape into it. And so that is for cutting things like threads. It's how we make very precise shafts and that sort of thing. And so we teach you how to do all kinds of manufacturing techniques in this course. I think it changes a little bit every year, but traditionally students make a clock. They make usually a tool like a screwdriver or a vise. And they also make some open-ended projects as well. So there's opportunities to learn both through structured activities in this lab that take things you learned from your classwork and apply them in the real world. And there's also open-ended design that let you explore and experience what you want to experience in this program. To steal another Steveism, it's kind of a choose your own adventure. So there's lots of room in this program to design and explore things that you're interested in. It's very much set up to enable you to do the thing with mechanical engineering that you want to do. So that's kind of the brief overview of the machine shop and the way that our manufacturing courses meet up with the real world manufacturing tools that we make available to you. So once you take the sophomore level Mech 200 class, you have access to this room to work on your projects, both for your coursework and for designs that you come up with on your own. So that's kind of the overview of Mech 200. Do you guys have any questions for me about this lab space or about this portion of the program before I move to the next one?
Any questions at all?
It doesn't necessarily have to be about this lab space.
Yeah, we'll talk. We've seen us do it.
Oh yeah. So. Well, I'm gonna pack up and move over to the materials lab next, I think, and we can talk about that.
So the Engineering Manufacturing Educational Center is a lab that is a little bit unique in our program in that it is something that you'll use as part of your sophomore Introduction to Manufacturing course, but then not only is it available to you, but you're expected to use it for the rest of your time. So whether you're in sophomore design, working on junior level projects, and senior design, if you get connected with a research lab, you're going to need to build a lot of things. And this is a world-class manufacturing space for you. There's a few other things that we couldn't see today, but we have a set of 4 vertical mills, which will also do some basic machining on. We also, on our Foothills campus, have a foundry, so you can cast your own brass and aluminum alloys. We can also get it hot enough to do some really basic casting on cast irons. Not quite hot enough for any steels yet, but one of these days we'll beef up the foundry. And as James kind of takes a really quick spin through the rest of the shop, you can see it's a rather large place. We have sheet metal, optics, rolling machines. We have a small injection molder. We have 3 3-axis CNCs. One has an add-on 4th axis. That's an oversized Lodge and Shipley lathe. We have furnaces. We have turret lathes for doing multiple operations. We do hardness testing. We do all kinds of things. And these are things that you would see in a general machine shop. So when you come through this program, manufacturing is one of the cornerstones of what we do in engineering, and you're going to be a basically competent machinist. We find that commonly, and this was my experience too going into industry, that when you go into a company, they might not have you actually doing machining, but you're often going to be the person working with everybody on the shop floor because you understand basic manufacturing processes. As part of the Introduction to Manufacturing course, you'll be building a clock that uses 18 discrete operations. So you'll be turning, drilling, threading, milling, counterboring, you're doing some basic CNC work. Often students will do individual CNC work, so you'll be trained on how to do a basic 3-axis program. We have a paint room, we have a welding room, we have all kinds of tools that are going to be at your disposal. So just keep in mind, this is, I won't say unique to engineering programs, but the scope and scale and access that you have in this with a full-time director, Doc Schaefer, who can teach you how to do just about any manufacturing process you can dream up is a unique thing. So this is something that we find our students are extremely successful for having gone through. And also just to have a shop that you can go in with your ideas, as long as it's somewhat school related, we can turn you loose and we're there to help you as well. So as James sets up, he's now across the hallway from Emec in our joint lab space we use for both materials and for our experimentation course where you learn how to acquire data. And so as James sets up, I will let him take back over.
Thanks, Steve. Give me just a moment here. We have some of our incredible TAs hard at work in here, so I want to set up in a place that's not too distracting for them and in their way.
If I can just say we have a couple questions in the chat also.
Absolutely. Let me find the chat. Okay, 5-axis CNC. We do not have a 5-axis CNC. We do have an add-on 4th axis, but a lot of the local companies we work with do a fair amount of 5-axis CNC work. So our students learn Mastercam and typically transition into those roles very well. If you're interested in doing complex machining, we'll get you our contact information. We can talk offline. There's a lot of options for doing that. Is there any access to the welding process? So we typically do small training sessions when we have interest. So if we have a group of students who want to do TIG welding, we can get 3 to 6 students together. We'll run just a quick seminar and teach you how to do the basics of TIG welding. And so we have capabilities for arc, MIG, TIG, and oxyacetylene welding. So that's one that we do just kind of by student demand. If you're already machinists, can you use the shop as a freshman? There are some things that you will be allowed to do as a freshman, but we do limit it a little bit because we need to make sure that you've gone through our training and safety process. It's not that we don't trust you, but it's just for your safety and liability purposes with the university. So again, that's one, as you come in, reach out to us. We'll be able to work with you to make sure that there's resources available. We probably won't be turning you loose on a CNC right away, but we can kind of assess your skills and come up with an individual plan for you to make sure that you have access. Let's see. And I think that covers the bulk of our questions. So James, take it away. Thank you, Michelle.
All right, so the next lab that I'm in, and this one is perhaps a little less visually impressive, but it is certainly no less fun and certainly no less impressive from an intellectual perspective, is our materials laboratory. This lab is, it's changed a lot since I was a student in this program in 2009, which to some of you may seem like a really long time ago, but the amount that this lab has changed just since then, I took the class, I would have been in 2011, is incredible. And we have really added to the capabilities of our materials testing program to where when you leave this, you'll have a good taste of what being a materials engineer is really like. And a lot of that is thanks to the hard work of our TAs and graduate students who came out of the program and said, you know, I think we can build on this foundation. So in this laboratory, you'll do a number of things. And with materials, so what materials testing is basically everything around you is, not basically, everything around you is made out of materials. And some of them are textiles, like your fabric mask, if you've been wearing one of these around. Some of them are polymers, like the power brick for the case anyways, the power brick on my computer. Some of them are metallics. Oops, I forgot to get those out. You know, like steel or aluminum, brass, ceramics. So everything around us is made out of stuff. And the thing we need to know about that stuff is what is it capable of doing? And mechanical engineers are, of course, interested in the mechanical properties of that stuff. How strong is it? How much can we stretch it out? How long will it last before it rusts away or corrodes? What kinds of failures will this stuff result in? So that we can make our designs using the right stuff. And so in this lab, we have lots of tools to help us understand more about that stuff and how we can change that stuff from maybe something that's less ideal to something that is more ideal, doing things like heat treatments and other hardening and materials modifications. And so this lab is kind of centered around teaching those concepts. And the really cool thing about materials properties is that this lab probably doesn't even qualify as a light introduction to materials properties. So if this is something that gets you excited, this lab has essentially unlimited room to grow and is available, like our Emec, for your use to explore properties of materials that interest you. And so we get regular, I would say, I don't know if Steve may have more comments. I haven't actually been around for like years, for example, but we get 2 or 3 requests a month to use this lab from undergraduate and graduate students who are conducting research on materials for their own purposes. So while this material is set up like materials lab is set up like a classroom, the things you learn and the tools you use are very much the real deal. And we're trying to equip, to inspire an interest in material sciences, because it is fascinating what materials science is capable of doing. It's an incredible area of research, and it's growing rapidly. I think it's one of the kind of the top, I think I read somewhere it was like maybe the top 3 or the top 5 most rapidly growing disciplines in engineering. And so this is a great introduction to how that works. I had considered setting up some demos. Some of the material science demos are a bit time consuming. The one that we're doing today, actually, it's a pretty neat one. Steve may have designed this one, so a little pitch to Steve, but essentially, all of our metallic materials are not just pure metals, but mixtures of metals. And so in this course, we learned about some of the materials properties of the different mixtures. So these are little cups of solder. I don't know if you can see that. You probably can't see that very well. It's a little grainy, but it's different alloys of metal, and we measure the temperature as they cool down. And that tells us something about the composition of this metallic. And then we can look at samples of that metallic material. Let me zoom around here.
Yeah, so what James is doing is going around to a microscope, doing what we call microscopy, which is an integral part of materials science as well.
So we would look at a tiny sample of that material, this puck here, and while this surface looks nearly mirror smooth to the eye, when you look at it under the microscope, you see that it is actually a maze or network of grains that connect to one another and interact. And the way that the size of those grains and the way they interact with each other says a lot about what this material is capable of doing from a strength perspective, from a heat transfer perspective, and other things. And so those are the kinds of things we teach you to do, both to understand analytically by reading and attending lectures, but practically by observing it with your own eyes. So you'll learn about this in the lecture, and then right away, you'll come to the lab and see the principles you learned in the lectures with your own eyes. And that's, again, a theme throughout this program, is that we want to educate using the best, get back into the window here. We want to educate using both the best classwork and text work available, but then back that up with the real world examples and experience that gives you a taste of how we know what we wrote in the textbook is true. And so the materials lab is a great example of that. It looks like we have a few more. Do we have any questions in the chat about this one?
We don't have any specific to materials. We did have a question about what CAD software we use. We have standardized SolidWorks across our program. In our Mech 201 design course, you will learn how to be a basic SolidWorks user. We also have options for certifications as part of that course. We do have several other CAD packages that are available, but SolidWorks is the standard one that we teach and is used for all of our modeling purposes. We also have a lot of students who do work in Fusion 360 and Mastercam and AutoCAD. We used to run Creo Parametric, but we've since gotten out of that as we find our industry partners generally have all switched over to SolidWorks. If you have been doing any CAD work and you have concerns about transitioning into SolidWorks, do not panic. If I can learn it, you can definitely learn it. And if you're well-versed in any one type of CAD software, it's generally a fairly easy transition into another one. It's just the functions are generally the same, the buttons are just in different places, and we'll be here to help you with that transition as well. And so as James is setting up, moving from our materials lab into our mechatronics lab, Just a few other quick words about the material science. Materials is its own wing of engineering, and it can become extremely complex. If it's an area that interests you, we have a lot of research labs you can get involved with, and there's 1,000 rabbit holes that you can go down. But the purpose of our Introduction to Materials course is to give you a very deep dive in one semester into what it is to be a materials engineer. There's material science, which is just the actual science of how materials interact, the capabilities that they have, and then the mechanics of materials, which we're more concerned with in engineering because, as we talked about before, we are using science to solve practical problems. So for us, it's just understanding what we can actually do with this to solve a problem, to build a shaft, to make a part, to conduct electricity or heat or whatever it's going to be. And so now we're transitioning into the Mechatronics Lab, so I'll let James take back over.
All right, so the Mechatronics Laboratory has a special place in my heart because when I was a grad student here at CSU, I was the TA for the Mechatronics Laboratory. And the other reason that I love the Mechatronics Lab is this is one of the few places where you will be assigned a project that is truly open-ended. Whatever you can imagine and whatever you can build, that's the project. And not only do we make a very broad, open-ended assignment, but we give you all the tools you need to succeed in that assignment. So this is bringing together things like the Materials Laboratory and the Emec Manufacturing Laboratory and our 3D printing lab, which we'll be going to next, as well as electronics and programming microcontrollers, all focusing on a project of your choosing. And it is not that often in life where somebody says, build whatever you want. So this is a special lab for me. And I loved my students' projects because there is incredible creativity in what you can do. And so I'll just give you a brief flavor example of the types of equipment that you'll be working with, the types of tools we have available, and how that project kind of shapes up. And unfortunately, there aren't too many of the projects hanging around because the students are usually pretty proud of them and they take them out. But maybe, I don't know if it's possible to post a link to the Mechatronics greatest of all time website. Is that possible, Steve? I mean, I should have asked this before bringing it up. You can definitely Google Mech 307 CSU and get to the website yourself, but maybe we can stick it in the chat or something.
I'll find it and post it in there, as well as the links to all these different undergraduate teaching labs that we're in. So James, you take it away. We'll have that up in a second.
Oh, thank you. So throughout the program, starting in your freshman year, so in your very first engineering class, you will get an Arduino. So some of you have probably already seen Arduinos in your high schools or even in your personal interest. And this is an incredibly powerful prototyping tool. I would have loved to have this much kind of processing power in a microprocessor. When I was going through the program, we used PICs, which are actually widely used in industry still today because they're very low cost, but they're not nearly as fun. So you'll receive an Arduino as part of your Mech 103 course. You'll receive another one in Mech 202, which is another design course. And then finally, when you land here at sort of the culmination of all the mechatronics, the electronic programming portion of our program in Mech 307, you'll receive yet another. And you'll receive a bunch of additional tools too. So you don't just get, you won't just have these available to you. You'll have all kinds of servos, stepper motors, brushless and brushed DC motors, actuators, LED lights, the works, everything you can think of to design your project. In the labs itself, we walk through good design practices. We walk through how to control things, specific types of things like servo motors and stepper motors, and those sorts of things. Control them well, not just kind of slap somebody's pre-made internet code on it, but actually understand what we want to accomplish in controlling that motor. And we use a ton of tools to do that. So behind me, you can see what looks like some older equipment. It is probably actually old, but you know, the fundamentals of electronic design hasn't changed a ton. And these tools are incredibly powerful for analyzing and diagnosing problems with electric circuits. So that's the other thing we do, is emphasize troubleshooting ability. because if there's not a problem in industry, you don't need a highly paid, highly skilled engineer to help you solve it. So a lot of different engineering jobs in industry center around finding problems with circuits or mechanical systems. And so we definitely have an emphasis on troubleshooting in this course and finding issues with code, finding issues with wiring, and finding mechanical issues as well. We'll use tools like the Elvis 2 boards. This is like a really fancy breadboard combined with data acquisition, combined with signal generator, which lets you, output different voltage signals like square waves or sine waves, and just a ton of tools all in one thing to help prototype your devices. And then you'll build devices. And actually just remember, so I don't have, other than a bunch of computers with lots of fun software on them, that about sums up the hardware in the Mechatronics Lab. But I was thinking, we've got the poster on the wall, and so we could just do like a brief flavor of the kinds of projects. So my project was, I had a friend who built a sophisticated laser tag system, all his own design from scratch. And we built a wirelessly controlled, so we had a joystick that connects to a wirelessly controlled turret for the laser tag system. And you would wear goggles, and we overlaid information from the turret, like heads-up display, on the video feed coming into the goggles. So that's an example of a project. Another group of students built an incredible, it's called an inverted pendulum. So it's a rigid bar, basically. They had a little table on the top that you could put a drink on, and it would drive around. But it just has two wheels at the bottom, and this thing could drive around. It could track an object and follow it, I believe, and a bunch of other things. So these projects are incredibly sophisticated, usually full of creativity, and tend to be quite functional. People design them around things that they're really passionate about, and we encourage and enable you to chase your passion with the tools that we have here. Which leads into maybe a quick kind of a side plug. So when you're, as an engineer, you're getting paid for your brain, and your brain is thinking up of all of these great things. But when you go work for a company, the company says, you used your brain on company time. That thought belongs to us now in intellectual property. CSU is very different, especially with the undergrad students. So CSU has, in my research, which is not exhaustive, but fairly extensive because I've had a startup company coming out of undergrad program, CSU has perhaps the most generous intellectual property rules around what you generate on campus. Essentially, if you generate it here, it belongs to you. And we even have resources to help you take those ideas and explore their commercial viability, understand the patent process. And so, coming out of a class like this, you've been given 3 years of incredible skills, and you're full of creativity because engineering is kind of the art of creating useful things. So we equip you to come up with great ideas, but we don't just stop there. We make sure that if it's a passion of yours, you have what you need to succeed, if that's in business or in patent or even just understanding those things. So this is a very hands-on, it's academically rigorous, it's very hands-on, but our goal is to equip you to succeed with the tools that you have in any direction that you take it. So that's kind of my plug for CSU from an IP perspective, especially knowing that I've worked with 3 student groups who have gone on to start companies out of this course. Their mechatronics final project was something that they wanted to try and commercialize. And we have the tools to kind of give you those resources. So if that's of interest to you, entrepreneurship, this course specifically and CSU in general offers some pretty great resources to help you do that.
And just to kind of follow up with what James is saying, it's true. I mean, your ideas are yours, and we'll make the resources of the teaching labs available to you to do further development on those. We have a CSU Ventures group who are phenomenal. They can help you figure out the viability of a product, help you with the patent work. I just found out yesterday a piece of equipment that we designed to help one specific researcher just got a provisional patent, and we're going to start licensing it. So you'll see behind James a poster of our top 10 projects of all time. That is on the link that I posted in the chat. This needs to be updated, but that is the two-wheeled drink cart that he was talking about. These are complex projects. These are things that are probably far beyond what you'll normally see in a senior design project at most programs. We have you doing this one semester your junior year. So not only are these resources available to you, this is the expectation that you're going to have the tools, but have the drive to step in and really do something impressive well before you actually left this program. So as James is getting into our idea to prototype lab, I'll hit a couple of quick questions. Yes, SolidWorks, you will have availability to a student license of SolidWorks. You can use it anywhere on campus, or we have ways that you can remote in to grab a license to use on your personal computer. Is there any capability to work with carbon fiber? Yes, and carbon fiber can be pretty messy, but generally working with carbon fiber and composites, we have capabilities for both within classes and outside of classes. Depending on your application, we would just kind of connect you with the resources as needed. James is about to show you a lot of what we're doing in 3D printing, so I'll let him take that. We had a question about transferring college classes. We have facilities for doing that, but it's going to be very specific to your situation. I'll make sure that you have James and I's contact info at the end of this. Reach out to us individually. We'll assess your individual situation and get you connected with the right people. You now have the links to the Mechatronics projects and a link to our general undergraduate teaching lab videos and information. And from here, I will let James take us into the idea to prototype lab.
All right, so this is our idea to prototype lab. And this is a really neat lab. It is focused on additive manufacturing. And additive manufacturing is the fancy kind of nerd term for 3D printing. And some of you may have already had some exposure to 3D printing through your high school programs, and we value that and want to build on that here in the Idea to Prototyping Lab. So this lab is not tied to a specific class. Instead, it is available for any student from freshman through senior year to basically take the training and then come in and use any of our wide number of additive manufacturing machines, our 3D printers. So the printer that we were just looking at is actually printing a part right now for our sophomore design competition. So this is somebody that has only been with in the mechanical engineering program for about 18 months. They've already designed a part in SolidWorks, sliced it in Cura, prepared it for 3D printing. This is actually their second print because it's a very complicated part and we had some problems with the first print. It was warping, which is why we put that, you might have noticed there's like kind of a shiny case around the printer so we can control the temperature inside the housing there and reduce warping. And this print, you know, it's quite interesting. 3D printing is often a very slow process. It's able to make shapes that are not physically possible through any other process. But this print has been going now for about 39 hours. It's actually down to the last 2 hours right now, which is sort of exciting. You know, it's like after almost 2 days of waiting, here we are in the final countdown. And so we have, so our standard printer here is a Prusa i3S. It's a pretty common printer. Some of you may even own one or a very similar one. But they've proven to be a reliable prototyping workhorse for us. But when you want to get more exotic, you know, we had the question about carbon fiber, and carbon fiber and fiber reinforced prints is kind of a cutting edge thing. There aren't. It's only been in the last couple of years that that's really been widely available. And so right behind me, let me make sure I don't knock the printer off after 40 hours of printing. This printer, there we go. This printer is called the MarkForge, and it is actually capable of printing with a carbon fiber toe. You can see, let's see if I can put this up here. There we go. All right, so right here is a spool of, can you see that? I can't really see the screen. Yeah, all right, perfect. Right here is the spool of carbon fiber, and it runs up through here and then gets extruded into the print during the print. And so the I2P lab can teach you how to design parts with integrated fiber reinforcement. which is sort of an up-and-coming area of additive manufacturing. This printer can produce parts that are on the order of the strength of aluminum, but do so using common polymers, common plastics with the carbon fiber embedded in it. We have other printers as well, not in this lab space, just because it's kind of a sticky, messy mess. But we have resin printers that are capable of incredible detail. I just helped to print an engagement ring for a student, a model of that. So it can produce, 3 to 5 micron level parts. That's very tiny. And we have large format printers. We have printers that can do very high temperature materials like PEEK plastic. This lab sort of has it all. We have a pretty cool printer. It can do a full color print. So if you design it in SolidWorks with all the different colors, you kind of paint up your model. You can print in full color. And this lab is available both for course projects and for person projects. So if you're into tabletop modeling, or you really like historical statues, you can see all around in here. These are just things that students were interested in, that they wanted to print, and so they just printed them. We've got statues, famous statues. I think from the Louvre and from other famous art museums. We've got mechanical examples. This is a pretty cool one. This is a working ratchet that somebody printed as like a single piece. So that's pretty impressive. Turbochargers. We have a printer that does the ceramic material. This is our full color printer. They printed this skull here, and it has it's anatomically correct. So medical students can use these prints to learn about the human body. We have, if you're into Star Wars, we've got more Baby Yoda prints than we know what to do with. So swing on by and pick yourself up a Baby Yoda from the I2P lab. If you need an Iron Man suit, we can do that. We printed an entire Iron Man suit, fully functional, as I understand. I believe the student commutes via Iron Man suit now. So this printing lab is really quite impressive. And it's fun to see. The printers are running almost all the time. It's a bit of a slow semester right now, but there is something new coming out of this lab every day, and it is a blast.
And James, we're starting to get a little bit short on time, so why don't we head on up to the Dynamics Lab?
Perfect.
And we don't have any other questions at the moment. If you do have them, please feel free to put them in the chat. But the I2P lab is, as James said, something that's an open, available resource to you. I'd love to say it's all done for academic purposes, but realistically, probably upwards of 2/3 of it is just for fun. He's not joking about the Baby Yodas. They're everywhere.
There's so many Baby Yodas. Steve, I left my keys.
Metal 3D printers. We are in talks to acquire a metal 3D printer. Unfortunately, with metal 3D printing, it currently uses, it takes up a little bit more space and power than we have available. But as we've been watching metal 3D printing, the size and the price of the machines is dropping drastically, and they're getting to a point where we can actually get smaller units very safely. So it's something that's on our radar. We're not quite there yet. We may have a metal 3D printing system coming online in the next few years with an industry partner. It'll be primarily used for research, but it is a truly impressive machine. The tough part is that you're typically doing some form of either depositing metal particles within some kind of a sort of a waxy, sticky stuff that holds it together, and then you put it in an oven, you burn off the wax, and you get to the sintering temperature, which is where the little pieces of metal are just starting to melt and they kind of connect with each other. They can also be done with lasers, but those are often using very fine metallic powder, which is extremely flammable. So it's not one where we can just kind of show up in the lab and park it in one day. There's a lot of infrastructure that goes into that. So it is something that we will have coming online in the next few years. If you're interested in that, we do work with a lot of industry partners that we can connect you with. One thing that we probably won't have too much time to get into today is the systems that we have where you can acquire skills that often translate into internships and co-ops, which can get you into areas where you can specialize and get actual meaningful experience as an undergraduate student, especially for traditional students. It's a huge program to take advantage of. And James is now in our Dynamics of Machines lab, so I will hand it back over to him.
Yeah, and Steve, just as a final comment on metal 3D printing, one of the things that I've been exploring and experimenting with over the last couple of months is there are now filaments that are embedded with metallic powder at a very high density. And so I've been exploring whether or not we have the capability already to print a part that can be sintered, which is a process where you print out the part and it's basically a plastic part with tons and tons of metal in the plastic. And then you send it out and they, in a very specialized furnace, heat the part up, burn away the plastic, and it leaves just the metal part. So it's not quite to the same level as a proper metal printer that Steve was talking about, but it would potentially allow us to produce metallic prototypes with our existing technologies. But the filament is brand new. I think it's only been around for about a year. To my knowledge, there's only one specialized printer that claims to be able to work with it. So it's a little bit experimental for us, but it's definitely a technology we want to bring online soon. So this is the lab that maybe most people think of when they think of mechanical engineers. And this is designing mechanical linkages, cams, and connections. And it's a pretty neat thing. There probably are other universities that teach this stuff through hands-on experience, and Steve would maybe be able to comment on that. I don't know who's doing this better than us, though. So what you do is learn about 4-bar linkages in your class, and then you come to lab and you actually design and build 4-bar linkages out of acrylic. You know, like these acrylic pieces, and test them on our linkage and cam testing. So this is a custom device where we actually use a touch screen, which is right in here, to measure the path that the 4-bar linkage or the cam traces out. And we can use that data to calculate or measure acceleration and displacement and all the things that we kind of care about when we're designing true mechanical linkages. And so you learn about this material and the theory behind the material and the math behind the material in your coursework. And then you come here and apply it in real life. And it's a pretty impressive lab. So we do cam design, I think this is an example of a cam that we've got here that would maybe be an example of a part in mass manufacturing, or an example of a part even in a car engine. You may have heard like that's sometimes a thing that gets thrown around in the car world. It's like, got dual overhead cams. It's a technology that's been around, I don't know, forever basically, but it's exciting. So they put it on the backs of cars still. So you learn how to design these in a way that gives them the best performance, the longest life, and accomplishes what you want it to accomplish. Same thing with the 4-bar linkages. When you learn what a 4-bar linkage is, then you'll just be walking around and you'll be like, oh, hey, there's a 4-bar linkage. Oh, there's another 4-bar linkage. I was just thinking, I moved a bunch of chairs with this truck, and the truck had one of those lift gate things that kind of can raise heavy objects up. Do you know what I'm talking about? And there's a 4-bar linkage right there. So there's just 4-bar linkages everywhere in life. And once you take this class, you'll just fall in love with 4-bar linkages. I promise you. It's my enthusiasm doesn't make sense to you until you've experienced the love that a 4-bar linkage can offer. It's better than a puppy. It's better than a puppy. We also do vibrations in this lab. We have some state-of-the-art vibration analysis, and that is truly a fascinating discipline all on its own. We even offer a senior level capstone, maybe not every semester, but at least fairly often, that is focused on understanding vibrations. And that is a big part of reliability engineering in manufacturing and factory environments, and really just a bunch of disciplines. So this lab is a ton of fun and very hands-on. And just as a kind of a shameless plug for Steve and I, your tireless, friendly lab support engineers, all of this stuff is sort of custom designed just for you to teach this to the best that we can. So this isn't really something that you could go buy, that other universities go buy. We thought of this stuff, you know, it was before my time, so I really can't take any credit. I'll maintain it for you though. I'll keep it good and ready for you when you join us in the fall, because it's really a pretty incredible course.
Yeah.
So,
James, we've got about 10 minutes left if we wanted to head over to the thermo lab.
Yeah, we do.
So kind of following up on what James was saying with making sure that we've got the technologies available for you to do the learning as an undergrad, there was one piece of equipment sitting in the Dynamics lab there. These are all sorts of different systems. We have a student who came up with an idea for a dynamic damper. And so we were able to get this piece of equipment right here, which actually measures performance of a dynamic damper in vehicle applications. It's going to be used by one of our myriad of automotive courses, but the student just had a wild idea and got into the shop, started machining parts. He's done a fair amount of 3D printing, and now he's actually got a working prototype that he's testing. I think will be in later this afternoon, doing damper testing on that piece of equipment. These are the things that we want to make sure we can do, support you if you have a rabbit hole that you want to go down, which kind of leads into one of the questions we have that a lot of colleges, only seniors are able to get into and work in the machine shop. Are underclassmen able to get hands-on? Yeah, if we only turn you loose as a senior, you're not going to be a good machinist by the time you graduate. So you'll be in the machine shop for introduction to manufacturing as a sophomore. And then with manufacturing, it's a little different in that it's a required course, but then that entire manufacturing lab is open to you for the rest of your time. So it's available and you're expected to use it. You'll have multiple courses where you'll need to be machining and prototyping and fixing and changing and iterating all the time. We do not have an automotive department. If you're interested in engines, you need to talk to James. We have an engines and energy conversion group at the Powerhouse Laboratory. So if you look up Colorado State University Powerhouse, you can see the phenomenal on James's jacket. He actually came to us from the Powerhouse doing a tremendous amount of engine testing. So we have a series of automotive engine design, automotive dynamic systems courses that you can take as undergraduates. And if you're interested in getting into engines, oh man, this is the rabbit hole you want to go down. We have many, many opportunities. So James is now in our thermal sciences lab, and I will hand the conversation back over to him.
Oh, if you like engines, you need to send me an email. We will talk engines until your ears fall off. Or mine. So this is just, I'm just going to walk through this lab because this lab is like, if you're into fluids or heat transfer, you know, like if you want to design airplane wings or heat exchangers, I don't know, maybe. Well, I won't put that on you. I don't know anybody who grew up and said, I want to design heat exchangers. They're awesome. This lab is a wonderland. We just have, it's like a maze of incredible things for heat transfer and thermodynamics, fluids, all kinds of stuff. We got a big wind tunnel over here. This is always a hit. There's a kind of a sample airfoil in there. Hopefully you can, is that coming through? Yeah, there we go. All right. See our little pitot tube? That's how we measure pressure.
And so in this lab, it's a lot of very large equipment. So you'll be working with pumps, with fluid systems, with transferring heat, with blower systems. We were just bringing on a new blower turbine lab. So we're actually using a turbo from a car, a small turbo system, and you actually go through and understand the thermodynamic properties of that. It's not always just as simple as hooking up a turbo, which puts you in a spot where you get to do the real hands-on learning. As James was saying, you know, if you're reading about waves, well, they're one thing to read in a textbook, but when you actually generate a standing wave, that's a whole nother world. When you're actually designing a pump curve, getting your delta P across a pump and your flow rates and understanding the viscosity of the fluid that's being used, you can do a lot with that pump. And this is a lab that's under a whole overhaul right now. That right there is our fluid tunnel. This is a new piece of equipment for us. It replaced a very old one that we were using. We have a lot of commissioning left to do on this one, but we're partnering with our civil engineering group who does a lot of fluids research as well. We're hoping in the next couple of years to actually attach a laser array on the back so that you can measure instantaneous turbulence. Turbulence is something that you're going to get into your junior year. Don't worry about it yet. It's complex, but it's a really, really cool thing. You don't even have to understand a lot about it to be able to use it as a great tool.
Get pumped for turbulence.
But we've got about 5 minutes left, so I think that gives you the flavor of what we're doing in these undergraduate teaching labs. So every lab that James has gone through is either available to you as a resource or as a required lab. You will go through and use all the equipment in that lab as a required course somewhere before your senior year in our program. We are the most hands-on program that we've seen anywhere, and we're continuing to develop. So right now, like where James is right now in the thermal lab, you can kind of see that large black tank that's over his shoulder. That was something that we used to set up a turbo machineries demonstration for one of our graduate level courses. We're always finding ways that we can implement more hands-on technology into all the things that we do. We do have a question, how does our program compare to UC Boulder? That's a great question. We are extremely hands-on. So what I would say is I have a cousin who went to CU Boulder at the same time I was back at CSU. He had one course where they built some kind of a truss or a beam that they did testing on, and that was it. That was all the hands-on. They do have a few things that are, they're a great program. I'm not going to beat them up. I'm going to beat them up a little bit because my cousin went there. But if you want to do hands-on application, we are clearly the school that you want to go to. You're going to come out of our program knowing how to do a whole lot more and probably for a whole lot less money, especially if you're an in-state student or a veteran. I mean, we are the best value you will find by a mile. If you can find a better value, let me know. I have not seen anything that comes out anywhere close. We also in this tour have not had time to go to all of these satellite campuses that are not on our main campus that you can be involved with. So especially with the research areas that we work with, you choose your level of involvement. If there's an area that you really want to get involved with and you show up at a research lab and just say, I'm going to volunteer and help you guys sweep the floors and take out the trash, but see what you do and learn about what this kind of research is, they will bring you in. And that's where you can start figuring out what you want to do as an engineer. The students who succeed in this program rarely are the brightest students coming in, but they're the hardest working, the students with no quit, and the students who will just show up and find places to get involved and gain practical skills. Having been on the recruiting side off in industry, it's a nightmare when you're trying to hire students into a job because you go through events, you have 300 resumes, you've got to get it down to 50 overnight, you're going to have phone calls with, and everybody's the same. Here's where I went to school, here's classes I took, here's my GPA. And it's really hard to differentiate one student from another. But if you were hired on as an undergraduate research technician in a lab, all of a sudden in a sea of gray widgets, you became a bright orange widget and people want to talk to you. They have questions and you can have opportunities that way. We talked about the powerhouse. We also had the Engineering Research Center in West Fort Collins. We have the Factory for Advanced Materials Research. We have a whole biomedical engineering wing. I'm sure you guys are getting some information about that today. A lot of our biomeds are dual degree with mechanical engineering. Our department head, Dr. Putlitz, has a phenomenal biomedical research lab. There are a million rabbit holes you can go down. And the more that you can self-specialize, the better engineer you'll be coming out of our program. And so James and I's job by extension is to find opportunities for you, if you're driven, if you want to show up and do something, to get you into a path where you can do the unorthodox, come find areas that really interest you. We did have one other question, an intercooler in the background. That is part of our Mech 38 thermal sciences course. So this is one that you'll take your junior year. We do work with that. That was part of the turbo demonstration that we're bringing online this semester. We have one part where you can actually use the intercooler to dump heat out of the system, and one where we can bypass the intercooler so you can measure the thermodynamics of the system without having that heat dump. So yes, you will be actually putting your hands on that equipment your junior year.
And Ben, with any luck, we will also have a small industrial diesel engine demo in here at that time as well. These labs take some time to develop. They're fairly sophisticated. And so it's not exactly a guarantee from me to you, but it's definitely something that we're, the timeline should have it in here in the next 1.5 to 2 years. So that is a portion of our work here in engine development, understanding engines, because that's a huge piece of thermodynamics. So.
And I think that about is the end of our time today. If anyone has any follow-up questions, James, I went ahead and put your email in the chat. Everyone's got my email and cell phone number in the chat. You're going to have questions. As those questions arise, reach out to us. We're very busy. It's common that we can't get back to you right away, but we will get back to you in a very timely manner because you're going to have a lot of questions about how you're going to fit into this strange puzzle that we built at Colorado State University. And there is a place for you. We just need you to show up with a great attitude and work your butt off. That's what we do here. And if you're willing to do that, I guarantee you this is a world-class education. We can open a lot of doors for you moving down the road. So, Jackie, I believe 9:15 is our cutoff. Is that correct? Wonderful. So we will end this session. You have our contact info. Hopefully we're able to answer some questions and give you some ideas about our program and what we do. And again, please reach out. We're here to answer you. This is my cell phone. You have the number. Generally, if I'm awake, I will get back to you. And we will see all of you next fall.
All right. Thank you.
All right. Thank you all.
Yeah, thank you.
Jackie, what's the next one going on? Or should we stick around if anybody has some offline questions?
Yeah, definitely. The next session starts at 9:20, and that will be the research experience session.
Oh, you guys want to get in that one? That's going to be great.
Oh, yeah.
Yeah, James and I both kind of got involved with research as undergraduates, and it's a lot of fun. It's a ton of work, but it's a lot of fun.
Awesome.
And
Yeah,
just-
thank you all so much. That was so great this morning.
Yeah, it was fun. These are a lot better when we can actually go in the lab and like set things on fire and smash stuff with hammers, but it's an okay second.
Well, cool.
And Summer, I see you on here. Did you have any follow-up questions?
No, I just wanted to say thank you.
Well, wonderful. Well, we're excited to see you coming back in the fall.
Yeah. All right. Have a nice day.
You too. And
Thank
we'll
you.
stick around until 9:20 if anyone does have any questions you'd like to ask us. Marcel,
Like-
I am dying to know what you're doing in the background there.
Yeah, me too.
I'll email you guys. I'll have to copy the email real quick. I'm just like in the middle of work, so.
That's okay. No, we're actually going to pick your brain. What I'm watching you do might actually tie into some lab development that we're currently working on. So we're going to chat.
Okay. All right. I'll shoot you an email right now. So you have actually, I'll just shoot you my email in the chat.
Cool. Perfect. And Eli, I think you had a couple of questions that were earlier about the SolidWorks and the design. Is there any follow-up that we can answer for you? Wonderful. Oh, we got it.
I'll
Thank you.
talk to you.
Aiden, thank you very much. We hope that we are your top choice. We do something that's pretty special here. This is pretty unique. And just as fair warning, if anybody's remaining, if you do end up with questions for me or James, we do have a tendency to, if you ask for a sandwich, we're going to like bring you the animal. So just bear with us if we maybe give you a little bit too much information right off the bat, but we get excited about this. It's a lot of fun, and doing hands-on application is kind of our specialization here. They don't give us a lot of adult supervision, so we get to kind of run amok.
Oh, yeah. It gets crazy. We have fun.
Yeah, well, you guys didn't even get to see the lab support office. That's kind of our little mad lair where we have a million little projects and a lot of stuff to work with.
Oh, man, it's bad right now, Steve. You go out of town for 3 days and trash the place.
Yeah, I'm just glad notice on my desk. I have possibly the worst desk in the department. Not quite in the college, but I'm in the running. So, well, wonderful. Well, if anybody doesn't have any more questions, it looks like we're rolling up on 9:20, so we'll turn you loose for the research experience, and we will see you all in the fall.
Thank you. See you soon.
All right, see ya.